Hi, welcome back. This is going to be talking about Introduction to Heat Transfers. This is a follow-up to the idea of thermodynamics. So now what we're going to talk about is transferring those heats and how fast they go. This is again in section 1.3.1. So now we got to go back and look at some previous equations that we have already talked about. And that is power. Power is heat over time. It's energy over time, or how fast we use up energy or gain that energy. Now, it also can be used in this equation. K, which is a thermal conductivity, how absorptive or how reflective it is towards heat, times the area, times how much time, the temperature difference, divided by the length of time, thickness of the material. You can rearrange it so you can just solve for K. So K is unique in that every property has its own K, and you have to get that experimentally. So let's look at a question. Calculate the energy transfer in a wall if the wall section measuring 2 meters by 1 meter by 0.04 meters thick with a thermal conductivity of 0.1. Opposing sides of the wall section have a temperature of 10 and 5 after 1 hour. So now we need to list all the knowns. We know the area, which is 2 times 1 is 2 meters squared. Thermal conductivity is already given to us in the problem at 0.1. The thickness of the material is only 4 centimeters or 0.04 meters, and the difference in temperature is 5 degrees, subtracting the 10 to 5. And the change in time is 1 hour, or converting that to seconds, 3,600 seconds. So now, what we're going to do is we need to first calculate our power. So here's our equations. Now what I want you guys to do is plug them in. Alright, so we're going to plug in our numbers to solve for Q. So we plug in their numbers to solve for Q. We plug in Q, power into this, rearranging the equation to get this one. Power times time is equal to energy, or the equation here times T. So now let's plug them in. K, 0.1 times the 2 times the 5 degrees change difference divided by the 4 centimeters in thickness, all multiplied by the time it took, and that gives us an energy of 90,000 joules or 90 kilojoules. Now we're going to move into something that's a little more fun, and it's called the U value. The U value is how it's called the coefficient of heat conductivity. It's the ability for something to conduct heat, and that is just equals to power over area times the difference in temperature. In the metric system, it's watts per meter square per degree Celsius, or in US, it's BTUs per square foot hour per Fahrenheit. Now, U is an inverse relationship to an R value, and that means just 1 over U is equal to R. So U is how conductive, R is the ability to resist the heat. When you have insulation, insulation has an R value to it, and that R value is going to allow you to know how insulative it is. So when you put insulation in your home or something like that, it's going to give you an R value. Now if you have several layers of insulation, maybe a brick wall plus styrofoam plus maybe some fiberglass batting plus wood plus drywall plus your paint, those all have their individual R values, and you just add them up to get your total R value. Again, and if you notice, it's just this is your U. So here we go. Determine the R value of the wall cavity. So right here, this section of the wall. Okay, you just add them all up, and there you go. You get 27.7. So you add the drywall 0.5, 19, 7.2, the air at 0.1, and then finally the brick. So now we can look at what is the R value of the studded location right here. So you again add all those up and you get 15.6. Notice that this number is significantly less because it doesn't have that fiberglass batting in there. Now that fiberglass is adding a ton of insulation. Now we're going to talk about thermal energy. radiation, heat giving off through the electromagnetic waves or through infrared light. Now, Mr. Stefan, he came up with the law, and it's this big, ugly looking equation. It's not as scary as it looks, but it's Stefan's constant, which is right here, times the area times E, which is the emissive constant, it's another constant, times the fourth power of the temperature difference. So that's kind of a different one we've seen before. Now, it's really interesting is that everybody gives off heat. Humans give off heat. We're warm-blooded. And here is a illustration of the Mall of America. It's in Minneapolis, Minnesota. This is the size of a traditional mall, and it's basically 4 malls put into one. There's an amusement park here, a bunch of stuff in here. I mean, it's massive. To walk around it would take you a full day just to visit all the stores. But during the post-Thanksgiving Black Friday to Christmas sales, the amount of human traffic in the Mall of America is so great that they actually have to turn on the AC to actually combat the humans producing their own body heat during a Minnesota winter in December. So you have to, when you're building architecture, you have to actually think of, is this building going to heat up because of humans? We can think of that in our classrooms during like these summers or late summers when school starts, as the school gets really hot because there's so many humans in it. So let's actually do that. Let's look at a human and how much heat do they have. So prior to dressing, a student watches the morning weather to decide what clothes to wear. The bedroom is 65 degrees and the student's skin is 91.4 degrees Fahrenheit. Determine the net energy transferred from the student's body during this 15 minutes spent watching the morning weather. So that letter E is at 0.9 and the surface area of a student is 1.3. So we add what we know, and I can imagine once you guys would know what's next. Solve the equation. Alright, so we put in that. Our power is that one with Stefan's constant, area times the emissivity times the fourth power of the temperature difference. We plug those in and we solve for the temperature difference, and then we to the fourth powered it and then eventually plug in all our numbers and we get a power of 103.92 watts, and then we take those and we multiply that by power, which is right here, times the 900 seconds, which is the 15 minutes, and we get 93,500 joules, or 93.5 kilojoules worth of energy that person just emitted by watching the weather for 15 minutes. Okay, now we can take this application into thermal energy. What you can do is you can look at these reflectors, these mirrors. They'll actually take sunlight, reflect it up into this machine right here, which has a liquid metal in it, usually liquid sodium, and it will actually transfer that heat down into the system where that liquid sodium heats up so hot it melts, and then they can use that to generate electricity. You can also do it in buildings and trying to figure out how much energy the thermal energy rises. So the top floors are going to get hotter than the bottom floors. How do you set up your air conditioning system like that? So here's some solar energy ideas you guys are probably fairly aware of. Electrical versus this one is not electrical. This is a solar. They have water going through here and that heats it up, solar heater. So those are different types. Now you got geothermal, taking the heat from the ground and turning into electricity. So up in Greenland and Iceland, specifically Iceland, has these giant geothermal plants that can produce electricity. So if you have any further questions, go ahead and ask your teacher.